Okay, welcome to this video for Chem 161, touching on some other content for Chapter 6, where we're talking about IMF specifically and how they relate to properties of water and by extension to other materials. So water, as you've seen in its chemical structure, is a bent molecular structure with two lone pairs at the top with an electron group geometry of tetrahedral. And so we note that there's a strong dipole pointing towards the top of the molecule as oriented this case. And for this reason, we would expect the oxygen area to be very delta minus and the bottom half of the molecule as oriented, very delta plus. So we know this to have a net dipole for the whole molecule, and therefore we know that this molecule is polar. So we would expect dipole-dipole interactions by that analysis. And after we recognize that the hydrogens are bonded to an oxygen, we are justified in predicting hydrogen bonding as well. So the hydrogen bond has significant implications on water, given that the water molecules will be attracted to one another by this hydrogen bond. Okay, so in liquid water, which tends to be where we mostly think about water, the diagram for that is here, and we see the water molecule represented by an oxygen red atom with two blue hydrogen atoms, and that feature repeats throughout the bulk of the liquid. The dashed lines indicate the hydrogen bonds that we've touched on here. So these are the hydrogen bonds. Recall this is an attraction of the oxygen on a neighboring atom for the hydrogen bonded to a neighboring oxygen atom on another molecule. And this attractive force is called a hydrogen bond, and it is not a covalent bond. Okay. As the temperature of water is cooled, an interesting transition occurs, and you know that as we go from the liquid state reversibly to the solid state, that we form ice. And so we see that description down here. When we form ice, this hydrogen bond helps organize the molecules into an extended and regular array as the ice crystals pack and extend. And so what ends up happening is you develop this sort of three-dimensional honeycomb-like pattern as the water molecules pack into this array. So the diagram above here in green and blue actually helps speak to the three-dimensionality of that pattern. The molecules of water behind those, the sort of plane of the screen, are shown as blue, whereas those that are in the plane of the screen are shown as green. And so hopefully you can see here that we have an extended structure, again with this three-dimensional honeycomb type pattern moving behind the page, in front of the page, and in the plane of the page. And what ends up happening is there's a large molecular kind of pocket in the void space there that is not occupied by the molecule. The hydrogen bond has sort of programmed for this void space, and this means that we have less atoms per unit volume and that we've changed the density as we go from liquid to solid. So the diagram at right for liquid water does a good job as it packs more molecules per unit volume. The same circle there is shown. I have more molecules of water in that circle than I do in the neighboring circle. And so this is helping me understand that we have a density difference. This would be higher density as I have more molecules per unit volume than this lower density. And as a consequence, we would expect that the lighter material, the less dense material, would float, just like a pool air toy on water at a pool. And so this is the reasoning why ice floats on liquid water, is because of the hydrogen bonding implications on the extended structure that packs water molecules into this lattice. Okay, so it is in maximizing the hydrogen bonds upon freezing that the density of the water decreases, and it results in a macroscopic result for us that we've all experienced, that ice will float on water. Okay, so that's an important implication of the structure of water on properties of water. Okay, and so we'll see here that the property of water also allows for certain compatibility of other materials, and so we'll also touch on in a moment here how water is regarded as nature's solvent. Okay, so let's just add some points here for the properties of water. Okay, so we've said that it's polar and there's going to be very strong, very high intermolecular forces as a result of the hydrogen bonding. And we've said that the density of water, so symbol rho, density of water in the solid state is less than the density of water in the liquid state. Further implications, in the liquid water, we expect high surface tension. So high surface tension is the ability of the liquid to adhere to itself rather than spreading thinly and maximizing surface area if it were in a puddle. So water tends to aggregate with itself and makes a very high tension liquid rather than spreading evenly. Okay, so we call that high surface tension. This is a property that's exploited by several insects that have learned to walk on the high surface tension water, given that water doesn't like to move out of the way for an insect to sink inside. This is also at play when we touch on meniscus effects, as we can look closely and watch water kind of climb the walls of a vessel. So perhaps you've seen this, where water will climb the walls of a vessel due to this hydrogen bonding intermolecular force. So there's two things at play here. There's both cohesion, where we're talking about how water is attracted to the glass. Okay, so the polarity of the glass and the polarity of the water result in cohesion. And then there's also adhesion, like glue, adhesion of water to water. And this meniscus is the result, and when the diameter of the structure is very small, so the glass tube that the water is in, we can even observe capillary action or capillary action, where the water can pull itself into the inside space of the small, narrow glass tube and fill it up automatically. Capillary action is also at play in delivering water up the length of certain plants and trees, given the sort of small diameter tunnels, if you want, within those trees. So clearly nature has evolved to exploit the intermolecular forces that are strong in water. Okay. So moving on, we'll now look at some other kind of properties of water that you're already familiar with. So we'll look at this kind of question. This is a moment where you may pause the video after reading and thinking about this question. So see if you can determine the answer here. Which of the following must occur if we're going to boil water? A, chemical bonds between hydrogen and oxygen must break to form hydrogen and oxygen gas, and those are the bubbles we have seen when we boil water. Is that true? Or B, bonds between individual molecules of water break and may lead to the gases that we observe when there's boiling? Or is it both of those that are true, that the gases we observe are both due to hydrogen and oxygen gas and a gas from answer B? Okay, so if you've had a chance to think about this question, hopefully you settled on this idea here, that we are not doing chemistry when we boil, so we are not observing a chemical change when we boil. We are simply breaking that hydrogen bond and establishing the water vapor that is the gas phase. And that happens at the hottest spot, so that'll be at the surface of the pan in contact with your heating element or flame on your stove. And those bubbles are lighter in density, more space between molecules, and so those bubbles rise. And that is the process of boiling that you've likely witnessed. Okay. Good. So let's move on to consider some other intermolecular forces. We've touched on three main ones so far. There's two more that we want to understand, and they're related to mixtures, more specifically. And so the first builds off the concepts of dissolving. And so we know water can act as a solvent. We mentioned this a moment ago. And it's one that nature's used to found out how to exploit. So it takes advantage of all the polar properties of water and can use the water to dissolve necessary essential molecules for life. And so we already know that water is a polar substance with a dipole. We saw that a moment ago. And so it makes sense that if we're going to have compatibility like we have between water and neighboring water molecules, that we might see that polar covalent and very high charge analogous materials like ionic solids would be compatible or dissolve in it. So remind yourself of sodium chloride, like we have over here, a cube of sodium chloride, where we have chloride atoms in yellow and sodium ions, I should say, chloride ions in yellow and sodium ions in orange, building up a cube of sodium chloride, and that will dissolve in water, as you know. What happens in that dissolving process is that water forms a sphere of hydration, as it's called, around the ions of that ionic compound. So you can see here that water will interact. So if this is a negatively charged chloride, the delta minus end of water is going to be away from that, and the delta plus side of water will be towards that. And we will build a repeat of that around that ion to ultimately hydrate that ion in full. So you see that kind of reflected here for the first shell of water, the first sphere of hydration of water around that chloride ion. And the opposite orientation will happen where there is sodium cations. So over here, where the oxygen of water will be more oriented towards that and help pull that out of the lattice and ultimately yield an equivalent structure, but with the water molecules flipped in orientation. So that is all the oxygen atoms pointed towards the sodium cation in that case. So here we have the initial kind of sphere of hydration for water. Because we have kind of an organized system there, and there is now some other dipoles, we might expect another layer of water to surround that and another layer of water to surround the chloride. And so we can build up kind of inner spheres and outer spheres of hydration by this mechanism, and ultimately more disordered and less kind of associated water is surrounding these spheres with an ion within them. Okay, and you can see here that we have quite a few interactions that result in this structure. Shown in the dashed green are ion dipole interactions. So those are those initial ones that we just highlighted for the process of dissolving sodium chloride. And you see those right in the inner sphere of hydration. They are where we have ions with discrete charge, -1 in this case for chloride, interacting with the delta plus of water, and that is our ion dipole interaction, an intermolecular force. That same feature is shown in the other ion that is hydrated. However, we've got the opposite sort of situation. We've got a discrete positive charge in the center, and the oxygen end of the bent water molecule interacting with that. And so that would be another ion dipole interaction. And like we've seen before for water that we use to explain how ice forms, in the shell of hydration and to the secondary shell or outer sphere of hydration, we're going to see dipole-dipole interactions, and those will persist all the way out into bulk water. So we've now just seen how ion dipole forces can result. We see that they're an attractive electrostatic interaction between a discrete charged ion. So like sodium is discretely charged at +1, chloride discretely charged at -1, and we need a molecule that has a dipole for this interaction. So thus the term dipole ion in the name. Okay, so these ion dipole forces are actually stronger than dipole-dipole interactions that we've seen before in compounds like HCl or even HBr, for example. Those dipole-dipole interactions that bring those molecules into contact with twins of themselves are weaker than the ion dipole. And this comes about from the fact that the ion has a discrete charge of -1, -2, -3, and could also be the same in positive sense, +1, +2, +3. So that greater and fully discrete charge is what leads to a stronger intermolecular force there. So that concept also gets kind of normalized, if you want, divided through by the overall volume of the ion. Okay, so you have to consider the charge value and the size of the ion to think about what's called charge density. So charge density goes proportional with the overall charge divided by the volume of the ion. Okay, so if we have a +1 charge but a very, very large cation, the overall charge density would be low. If we have twofold charge and we have a very, very small cation, like magnesium 2+, then that's going to be a very high charge density. Okay, and so this would lead to, if we had magnesium 2+, this would lead to a very strong influence from the ion portion of that for ion dipole forces. Okay, the other interaction what we'll bring into play here is the dipole-induced dipole attraction. So an isolated oxygen atom with water will be our example for this. And so if water is isolated from water, we would expect a non-polar result given the symmetry in that molecule and the fact that oxygen is just as electronegative as its neighboring oxygen. However, since we know that water has a permanent dipole, that dipole can actually polarize or influence the electron cloud with a neighboring dissolved oxygen molecule. So that is to say, the delta minus on the water molecule will program, it will influence the electron cloud shown in red to repel that electron cloud away from an oxygen that is nearest that oxygen. So it will shift electron cloud away, lead to a delta plus, and this will be our dipole-induced result. So a dipole-induced dipole attraction. And so as a consequence, we end up with a shift in the electron cloud and therefore delta minus to the other side of the O2 molecule in this case. Okay, so in this case, we've described how water dipole creates a temporary dipole in a non-polar molecule. And we can observe, therefore, some compatibility owing to the bonding between the two, or the attractive force between the two. And this leads to some interesting properties that you wouldn't otherwise expect. So since oxygen is at first glance nonpolar, there will be some of the oxygen that can compatibilize with the water that is polar because of this induced dipole effect. And this is what leads to a little bit of solubility, allowing the oxygen to dissolve in water. And this is something that's essential for a lot of aquatic life, being able to access dissolved oxygen in water. And it's the dipole-induced dipole attractive force that allows for this dissolving of oxygen in water. Okay, so with that, we've touched on a lot of different intermolecular forces. We've seen the weakest, the London dispersion forces, very weak on our scale here. We've seen dipole-dipole interactions like we would see in things like HCl or HBr. Stronger than that is the hydrogen bonding case. We saw that. You can see here that the ion dipole that we touched on a moment ago for getting sodium ions dissolved in water, those ion dipole interactions in the inner hydration sphere are stronger and competitive in strength with that of hydrogen bonds. And ultimately, things like covalent bonds to orient yourself are known to be much stronger than all of these. These are the ones that hold the actual atoms together in molecules. And the ion-ion attractive forces that exist in ionic compounds in the solid are competitive with those as well. Okay, so that's sort of how we kind of rank them. Notice that we've been talking about intermolecular forces, forces between molecules that are kind of more moderate or weak. And the stronger ones are regarded as intramolecular forces, more commonly referred to as either ionic bonds or covalent bonds. And to further orient you, there are some even stronger bonds that we didn't get to touch on, which are covalent network solids, where we extend covalent bonds in 3 dimensions, like you see in diamond, where a tetrahedral environment exists at every carbon center. Okay, so I think we'll